So this is a piece of a pyrolytic graphite sheet, also known as PGS, and it's basically a very flexible form of graphite, and it has some very unique properties, one of which being that it conducts heat much better in the X and Y axis than through its Z axis. Or in other words, it can conduct heat much better along its length and width than through its thickness. It is also very good at conducting electricity and has basically all of the same properties as normal graphite. So for this reason, I will be using it for my little experiment here to see how it performs when used in a battery cell. So here I have almost everything needed to make a functional zinc-carbon battery cell. So I will begin by going over each one and how they're going to come together to form a battery. So first is a very fine graphite powder, which I made by dragging a razor blade against a little plate of graphite. Next is zinc metal, which will be the negative electrode and anode of the battery, followed by manganese dioxide, MnO2, which will be the cathode material of the battery. Next is the piece of pyrolytic graphite sheet, which will be the current collector for the battery or the positive electrode. And finally, we have the separator materials, which are needed to separate the two halves of the battery. And then lastly is the electrolyte, which I will be preparing later. So zinc-carbon batteries can have one of two electrolytes, with the first one that I'm going to be using today being ammonium chloride, and the second one, which I unfortunately do not have on hand right now, being zinc chloride. So here I've drawn out how I plan to stack everything together, with the zinc being the negative electrode and the anode, and the graphite sheet being the current collector, with the cathode material being the manganese dioxide mixed with the graphite powder, which will be sprinkled onto the porous surface of this absorbent material. So the shell will be made of 3 different pieces, 2 half-cell pieces, one for the negative and one for the positive electrode, and then a central piece that will firmly hold the two together. So here is what the half-cell pieces look like up close, and you may notice that each one has a little slot here as well as a half circle. And you may notice that when I bring the two together, the two half circles join to make a perfect circle. And then taking a look at the centerpiece again, which also has a hole in the center, it becomes quite clear that the two holes are meant to align. Which brings me to the little half-cell pieces here, which have a little slot, which are meant to hold the positive or negative electrodes. So the one that I just put in was the negative zinc electrode, and then next is the graphite electrode, where it will very simply slide into this little holder here, if I can get it to fit. There we go. So it's a perfect fit. It's a little bit loose on the graphite one, but that should be fine. And then the two half cells are brought together to form a single unit and then put into the central piece here. And the lights that I have overhead are making my hands kind of sweaty, but here I will try to fit it into the central piece. So here is the first half, and then for the second half. So I have the second half cell here and sliding that in like that. So with the two now perfectly aligned, you may notice that not only is the hole going straight through, but also the two slots here are coming out just enough to provide clearance for the two electrodes. So just to quickly demonstrate it, if I have the zinc electrode here, it'll fit in just perfectly like that. And then for the graphite, just very gently sliding it into that second piece right there. So I have cut my two separator materials to fit perfectly into the shells I'll be using for my half cells. So here I have one with the zinc electrode, and if I put the little piece of paper here, it'll fit perfectly inside of this. And then following that up with the little absorbent pad, putting that in, and it fits right on top of that paper just perfectly. So I will be placing enough material on both of the electrodes to provide a good amount of force between them. Which finally brings me to the dual purpose of the hole here, which is to not only allow for the electrolyte to be inserted, but also for any gases to be released. So the way the electrolyte will be inserted is using a special syringe that is used for refilling printer ink. Here's what the syringe looks like. It's basically a quite wide hole in the center, and I have 3D printed this and designed it to have a very snug fit for this little syringe here. So the way I plan to do this is by making a very small amount of electrolyte and then using the syringe here to take out a very small amount, and then taking the cell here, and very similar to a real printer ink cartridge, I will just put it into this little hole here and inject it inside of the cell. So with all of that now explained, it's time to start putting the battery together. So I will now prepare the cathode material by combining 3 parts manganese dioxide and 2 parts graphite. Okay, so here I have about 3 parts of manganese dioxide, or MnO2, and just over 2 parts of graphite. And I will very gently put it into this tiny beaker here, making sure to pick it up very, very gently. So I'm going to do this for about 1 or 2 minutes, making sure to go very slowly. Then doing a tiny, tiny bit with the stir rod, very gently. And you can see how lightweight that graphite powder is, that it's sticking to the walls here. So with the cathode material now prepared, it's time to start assembling the battery. So I will begin by assembling the positive side of the battery first, which will consist of the graphite sheet, the MnO2 and graphite as the cathode material, as well as the separators and absorbent material. And I have to do this very carefully because once the powder is on top of the graphite there and all of these are stuck on with some glue, there is no going back. And right before I start, because I noticed that the paper here is just a little bit smaller than the little shell here, I very carefully cut a piece of paper that should just barely be big enough to fit into this piece here. And I don't want to put it in because it's not going to come back out, but this should hopefully stop the powder from spilling out when it's all in and against the graphite. So I will begin the assembly by inserting this graphite sheet right into that slot there. So that looks pretty nice. Okay, so everything is now in place, and I am extremely nervous because I really don't want to ruin this. Okay, so I just decided to use the stir rod to drag the powder out so that the graphite and MnO2 do not separate, because the density of the graphite is quite a bit less than the MnO2. Putting a decent amount, but not too much. So I think that should be good. And to make sure it's all even, I'm going to put something on top and tap it with the stir rod. Okay, so all I could find was this heatsink here. Just putting that on top and using the glue stick or something to... So I'm going to add a tiny bit more. Or you know what? I'm just going to add the whole thing. And just leaving a little bit in case I need a tiny bit more. And that looks much nicer, but it still hasn't really spread out. So I think what I'm going to do is go and find like an old gift card or something and cut it into a small piece and use it to like pack it down evenly. Okay, so I've cut a piece of an old gift card here and it fits just perfectly inside of this half here. So I will use this to compact the powder down and get it all even. Okay, so that looks pretty good to me. Now it's time to put on this piece of paper here and put it to basically plug the powder and prevent it from coming out. Okay, so that's on there pretty good. So now I'm going to start and assemble the stack that's going to go on top of the paper here. Okay, so for this step, I'm going to put 3 pieces of paper and then 1 to 3 pieces of this absorbance material. And I will put a small strip of glue down the center of each strip, both to hold them together and to sort of act like a thickening agent. So that's 3 sheets, and now for the absorbance material. So that's 2, and now for the third one. So here's what it looks like up close, and I'm going to add maybe 2 more pieces to make it a little bit thicker. Okay, so this is 3 pieces of paper and 5 pieces of the absorbance material. So I will now use scissors to trim the sides. So with everything trimmed and ready to go, I will now insert it into the half cell. That is a perfect fit. Look at that, that's beautiful. And now I can compact the powder down actually by pushing on here, and that'll help prevent it from spilling out. Okay, so this looks pretty nice. Here's what it looks like up close. That looks very, very nice. Now I would like it to come up to this half circle here, so I might cut 1 more piece of paper to basically plug this and prevent the powder from coming out from the sides. So now I'm going to trim it and put it onto the cell here. It is in beautifully, and it is reaching up to the half circle so that when I put the electrolyte in, it will soak it all up. So with the cathode half cell now finished, it is time to start making the anode half cell. Okay, so for the anode here, it's going to be the same thing with 3 pieces of paper and enough of the absorbance material to stick up and reach to the top of the half circle here. So I'm going to start by buffing the surface with a piece of ceramic fiber. It's something I discovered by accident, but basically it works like those magic erasers, but for like metal and stuff. It's quite useful for stuff like copper too. Okay, so the zinc here is ready to be inserted. So just putting this into the shell, like that. That looks pretty nice. And now to glue together 3 sheets of the paper. So this is now 3 sheets of paper, so now it's time to add the absorbance material. So I'm going to put 4 pieces of the absorbance material on top of the paper here. And number 4. So just like the other one, I'm going to trim the excess off, but here's what it looks like up close. It is 3 sheets of paper and 4 sheets of the absorbance material. So it looks like it needs maybe 3 more sheets, 2 to 3 more sheets to raise it up to the half circle here. Okay, so this is what it looks like up close with the excess trimmed off. I'm now going to put it into the negative side of the half cell. Okay, so there is a tiny bit of glue on the bottom here, and I will now put it on against the zinc. Okay, so here's what it looks like up close. It is basically almost sticking up to the half circle here. I might add one sheet of a thicker version of this just to get it all the way up to this, to the top of the ledge here. Okay, so now it should be reaching all the way up to this ledge here, which it is, and it's sticking out even a little bit more, which is even better. So here's what it looks like from the side, sticking out just a tiny bit more so that when the two halves are joined, it's providing a good amount of compression between the two. So here are the two half cells side by side. So I think now it's time to join these two together using the center housing here. So I'm going to go with the zinc half first because there's nothing to spill out on the zinc side, but once that is inserted, then I'm going to go with the other half. So I need to be very, very gentle with this, making sure to align the half circle in the hole. Okay, I heard a click. Just going a tiny bit more, making sure it's all even. So now it's time to insert the other half. So this is the most critical part. I need to be very, very gentle with this. So this is what I was saying about the graphite being glued on. So going very, very gently, making sure the half circle and the hole are aligned. Very, very gently. Beautiful. That went on perfectly. And it looks like the things are aligned. So here is the completed cell. It is now all finished and ready for testing. So what I might do is apply some rubber adhesive around the edges here to prevent the electrolyte from leaking out when testing. Okay, so I've got some rubber cement here and a matchstick, and I'm going to use it to go all the way around the ledges here. And this will prevent the electrolyte from leaking out and the pieces from moving out of their positions. So I'm going to leave this to dry out overnight, and then I am going to prepare a small batch of ammonium chloride electrolyte and use that printer ink syringe to inject it into this little battery cell here, and then see how many volts it makes, how much current it can provide. So I'm going to come back when it's all dry and ready to go. So now that the most difficult part of the build is over, it's now time to start preparing to test it. So there's two things we need to do for this. The first one is to find a way to connect leads to the electrodes without stressing them or damaging them. And second is to prepare the electrolyte. So I think first I'm going to start by going over how I'm going to connect to the zinc electrode. So for the zinc, I'll be using these clamp type, I think they're fuse connectors or something. If I remember what they are, or if I can find it, I will put it here. So then we're left with the graphite electrode, because this one is very, very, very delicate. So I can't use anything similar to this because that would just ruin the electrode. So I need to be more gentle, but still not too gentle to the point where it would increase resistance. So taking inspiration from the way these connectors worked, I took some copper foil that I have a big roll of, and I cut out a piece that was approximately the same width as my graphite electrode. And after that, taking advantage of the very mild leaf spring properties of the copper, I bent enough of the copper to be approximately the same height as the graphite electrode, and I bent it down and crimped it with pliers. The way this is going to work is if I take this paper out, there is a tiny gap that should allow me to insert the graphite. So to make sure I don't accidentally damage the graphite, I'm going to put a piece of paper here as a placeholder, move it to the other side, just to keep the flap open a tiny bit. And then I'm going to put the graphite in. For a second there, I thought it ripped, but I finally got it underneath of this little flap here, making sure it's centered, and I don't want to put too much force onto this graphite here, but I do need to make sure it goes all the way in for the best amount of contact. There we go, that should be good. And just to make sure it doesn't come loose, I'm going to put some polyamide or Kapton tape right over top of that to hold it in place. Okay, so with the tape now put on to secure the piece of copper to the graphite, it is time to attach the little zinc connector. Zinc is also now connected. Okay, so finally, after hours of working on this, the battery is now finished and ready for actually testing it. So now it's on to preparing our electrolyte solution of ammonium chloride. So I'm going to begin with the preparation of the electrolyte solution. So before I can start actually mixing the water and the ammonium chloride, first I need to pick a concentration of solution. For today's experiment, it's going to be either 2 or 2.5 moles per liter with a solution volume of 8 to 10 milliliters. So I think I'm going to go with the 10 milliliter, 2.5 molar concentration, which will require 1.34 grams of the solute, which in this case is our ammonium chloride. I will begin by measuring out about 8 milliliters of water, to which I will add the ammonium chloride and then top it up to the 10 milliliter mark. So carefully measuring out about 8 milliliters of distilled water. So with the water now in the beaker, it's time to measure out the proper amount of ammonium chloride and add it to the water. So here I've measured out about 1.34 grams of ammonium chloride powder, which I will now add to the water. So with all of the ammonium chloride now dissolved, I will now add the solution back into the graduated cylinder and check the volume. Okay, so the solution is exactly at the 10 milliliter mark. So I will now move the, or transfer the solution into a small glass container that has a lid. So just simply transferring this over. So here is our 10 milliliters of ammonium chloride solution with a concentration of 2.5 moles per liter. So with the electrolyte solution now prepared, it is now time to move on to the next step for testing out this 3D printed battery. So finally, it's time to start setting up the test. So here I've got the battery in its dry state, the electrolyte we just made, the printer ink refill syringe, and a little wire I made to plug onto the terminal here. And let me get it focused. Just like that, onto the copper foil. So now it's time to set up the multimeters so that we can see how this battery works. And then for measuring the current, I'll be using 47 and or 4.7 ohm resistors. So finally, with everything now set up, it's the part we've all been waiting for, joining the electrolyte and the dry cell to see whether all of the work that went into making not only the cell, but designing the shell that the cell is using in 3D CAD was worth it or not. And right before continuing, I'm going to make a prediction of how it's going to turn out. So I am predicting that it's not going to make as high of a voltage as I would like it to because I am kind of concerned about the amount of force between the two halves when they were assembled. So that's enough talking for now. Let's get to actually testing the battery and connecting it to the multimeter to see how it performs. So first I will have to inject the electrolyte before I connect the leads. So I have a little protective film here that I put to prevent anything from getting inside. So just taking that off, like that. Is it going to completely fail, or is it going to work as intended? So I will take about 1.5 to 2 milliliters of the electrolyte solution. I am very nervous right now. Let's see if it was all worth it. Oh, it's absorbing. Okay, that's good. So with the multimeter now turned on, let's take a voltage reading. And it does take a couple of minutes for the voltage to climb up, but let's see what we have right now. So connecting the negative lead to our zinc anode, and then finally our positive lead. Let's see how many volts we have. Oh, 1.4. Is it actually going to work as designed? So now let's connect one of my 50 ohm resistors and see how much current this battery can provide. So let's see how it does. Wow. On my previous test, I'm going to disconnect it. On my previous test, I could barely get over 5 milliamps. Now we're getting like almost 20. 16 milliamps. So I'm going to disconnect it and very quickly go and calculate the internal resistance given that current. So right before doing the current test again, let's check the voltage again. 1.25 volts. Okay. 47 ohm resistor, going again. 18.3. Let me touch the wires here and see if that makes a difference. So this is actually pretty good. If I had made 2 cells and put them in series, this would be more than enough to power an LED. But for a future video, in the near future, I will very likely be making several of these and putting them into series to see how long it can power an LED. So it seems to be around 13.5 milliamps now. Let's check the voltage again. Down to about 1 volt. I think it might need more electrolyte. Okay, so with the electrolyte now topped off, let's reconnect the leads and see what we get. 1.13, 1.14. So it's climbing back up. As soon as it gets to 1.15, I'm going to switch over to the resistor again. Let's see what we get now. About the same. Let me see if touching this connection here makes a difference. Nope, the clamp seems to be doing a pretty good job. Let's go back to voltage mode. And let's see what we have. About 1 volt. So at 1 volt cell voltage, it's providing around 13 milliamps. Pretty good. Since I don't have a whole lot of cathode material on the inside either, so it is performing pretty decently. It is performing much better than I thought it would, and thankfully my prediction was wrong, so it's working very well. So let's check the voltage again when it gets to 11 milliamps. 0.96 volts. Nice. 0.97. It's going to keep climbing again. So the voltage after like 1 minute is up to 1.07 again. So now let's test the 4.7 ohm resistor. And my voice kind of sounds weird because I'm kind of getting sick. I'm noticing that when I'm talking kind of sounds anyways, let's see how much current. Oh, overload. That's good, that's good. Whoa, 38 milliamps. That was unexpected. Okay, that is very impressive. Let's go again. 34 peak, about 30 milliamps. So connecting that again. Yeah, about 30 milliamps. So let's check the voltage again. .94 and climbing. 0.95. Okay, I've got a 220 ohm resistor. Connecting that, and now let's see how many milliamps. 3.5, but it's still not staying stable. So after about 10 minutes or so, the cell is back up to 1.165 volts. And let's connect the 220 ohm. See if it stays stable. And real quick, I had a pretty cool idea on how to use these. I might make 2 of these and then put them in series and then use it to power a real-time clock chip. For example, like the DS1302. And for a project like that, I would probably make little rubber plugs to plug the fill hole so that the electrolyte doesn't evaporate. And I'm going to finish up the video by doing a short circuit current check for this battery, because it really cannot give that much current. So if I connect it directly to the ammeter here, it's not going to burn out the fuse. It's just going to give like 40, 50 milliamps or something. Connecting with no resistance in 3, 2, 1. That was kind of underwhelming, like 24 milliamps. So again, if this was a cool or interesting video in any way, please do consider leaving a like and or subscribing. Because seeing not only the subscriber count, but also the comments that people leave is really what gives me the motivation to want to make more of these. So thank you for watching, and for the rest of the video where it's going to basically show the cell discharging, I'm going to put like royalty-free music or something.